of using logic. Okay, there's a 4 and a 9 there. We're thinking D. But keep building off what Bree was talking about. And other groups now have this.
Oh, alright. Wait, like what I was saying, like 4 is now.
Yeah.
Okay.
Yeah.
So when we have you guys ever seen something like this before? F of X? So, what we were talking about yesterday when we had our tables, and we were plugging in a number to see if our equation was correct. Do you guys remember that? We had 3x plus 4 or something, and we were trying to make it match and make sure that was the correct equation. So that, here, what this is saying is f of 4 is equal to 9. So now this 4 is my x value. So you know we said x is a variable. It can change. Now we know x is 4. So what do we need? How do we find our answer from that? If our f of 4 equals 9, what does that mean these equations have to satisfy?
Can I pause one thing? I just want to point this out because this is I heard this I think from every group. None of y'all read this as f of 4. How do we all read this to start? F times 4. Which again, is that logical? Does that make sense based on things we've learned in math? Why would that make sense?
When you put a variable over it's times.
Right? And when there's the parentheses right next to something, it's typically meant times, right? By the way, you're going to need to write this down in a second, so pay attention to the conversation. But please notice that Ms. Kowalski is perfectly explaining this, and we need to emphasize it like it's read as f of x. F of 4. So what is my x now?
Yeah, so my x is now 4. So what does that mean about these equations? If my x is now 4, and we're saying f of 4 equals 9, and we need to figure out which equation is f of 4 equals 9, what does that mean?
No.
No? That's okay. What? What do you mean, like?
A.
So, A, we're on the right track, but why is it A?
Because 4 squared is what, 16? 4 squared equals 7.
Right, so f of 4 is equal to 4 squared minus 7, and you guys just said it, 16 minus 7 is what?
9.
So that means in this equation, when f is 4, this satisfies that equals 9. So A is our answer. But do you guys see why we plug that x value into the equation to get what our answer is? Okay.
Yeah, sorry, I have it still up there because I was doing attendance. There was something I was going to say really quickly and I can't remember. Oh, y'all said 4 squared is 16. Why is it 16? And then please pay attention, I'm asking this why because it's going to be helpful for what we talk about later today. Why is 4 squared 16?
Because squaring is the number times the number.
So when we have an exponent, it's repeated what?
Multiplication.
Repeated multiplication. I need you to hold on to that, okay? Remember, multiplication on its own is repeated what? Addition, right? When we just multiply, repeated addition. 3 times 4 is 4 plus 4 plus 4. But when we say 3 to the 4th power, that exponent is repeated multiplication. We need you to hold on to that for the rest of the day, sorry. So we're missing Jack, Zai, and Jordan. Those are the only 3, right? Oh, we were missing 3? For some right? Okay. Sorry. I should have used my book when I did that. Here you go. By the way, we did pick this one, this particular problem, because that's one of the first 10 ACT math questions in the April 2024 test. So I just want you to start, we're going to use ACT Wednesday to help us practice some of those things, especially because a lot of us are juniors getting ready for that ACT that y'all have in April, right? So we're going to pull a whole lot of ACT questions every Wednesday to help us prepare for the day and also to prepare for that test. Like, that's something that we need to hold on to. We're gonna use it, we're gonna apply it, it's something every single one of you is capable of. So let's make sure we master those things.
Alright, you guys did get your Frayer models today. They're in that, you have a packet on your desk, they're like behind that front sheet. We're gonna go over those in a second. That thing we did yesterday, what comes next, what comes later, we're gonna go back over that quickly and finish it, and then we have those front 2 pages are practice with all the representations we've been talking about. Alright, so, yeah. Alright, so yesterday we were talking about relations, right? And we didn't really define a relation yet. We were just think of what we've been talking about. So, a relation, does anyone have a guess at what a relation is? Based on the word? Huh? Something that's related? What'd you say, John? Connection. Alright. So, a relation, I'm going to use that word, connection. You are connecting inputs to outputs. Do we know what that means? Your X and Y. So, that question we did to start with, what would this 4 be? If we're talking about inputs and outputs. Input, right? It is what you are putting into the equation. It is what you're putting in as your X value, which is what kind of variable? It is an X variable, but there are 2 terms we've been using. They use them in science class sometimes. I and a D. Yes, our independent variable. We change it. It's our input also. Easy. Yeah. And then which one would this be? Your output, right? It is what is coming out of the equation after you put your input in. So a relation is just mapping inputs to outputs. Okay? Makes sense? Checks out? A function.
Can you just write that all the way out
Oh,
so
yeah.
we can write that on the Frayer?
Oh yeah, you guys should have a Frayer model.
I'd say there's a Frayer model, was it relations and functions or something like that? It's the very first of the Frayer models. Function, yeah, that one. Functions and mathematical representations. Thank you. So remember, look at the side that does not have the answers. Look at the side that is blank. So these are also check your understanding questions. Hold up, what was the next card? Do you know?
Jack.
Alright, so Jack's. Remember, these Frayer models have check your understanding questions for you to practice with, but practice only helps if you are checking yourself. KJ, you awake back there? Okay. You just made me a little nervous. Can you please write this definition down? Thank you, sir. They only help if you actually are checking yourself. That's why the solutions are on the back, the answers are on the back. Most of the time, you need to do check your understanding on your own. Keep that in mind.
What do we think a function is?
What do we remember about this?
What?
An equation.
An equation? Okay. There's more to it than that. A function, yes, can be an equation,
I would say that's
but
one.
it can also be in your graph.
What's another way you can represent a function? Equations, graphs. Say it louder, I heard someone.
Tables.
Oh. Any others?
Graphs. Pictures.
There we go.
Verbal. Perfect. So that's how we can display functions. But what is a function? Like, what is that? Does anybody have an idea of what that definition would be? No. So, it relates, funny enough, it relates to a relation. They are similar. There's just one key difference, and it's that for every input, there is only one output. Okay?
And I will say this, it's not just that they're related. A function is a special type of relation. So I might start that. It's a relation for such that.
Oh.
Right? So maybe right just above it. above the 4, yeah, there you go. It's important to recognize that it is a relation. Because what's the only thing that has to be true for it to be a relation, Caleb? It has to be two things. What are the two things? Okay, it's got to have an input and an output, right? The function is a special situation with that definition.
So it's a relation such that for every input there is only one output. And there are a couple ways we'll show you how on a graph, like how to easily identify that. We'll go over it later. But that is the definition of a function. We already went over our mathematical representations, just talked about those. What is the difference between linear and exponential? Linear is straight line. What else is there about linear? Come on guys, that's all we've talked about for the last 2 days. What makes a linear function? How do we know it's linear? Huh? Repeated addition. Anything else? Okay. Repeated addition, it's a line. Is there a certain slope rise over run? Is there a certain thing that pops into our head? Like an equation we talk about a lot. Y equals mx plus b. Perfect. All right, what about exponential functions? Repeated multiplication, multiplicative rate of change, all that good stuff. Okay. We do these now? You don't
I
have to
would,
do these
yeah.
now? Okay. All right, so y'all have your square model functions and mathematical representations. We should have been writing on this for these definitions. Do we have these down? Can I erase the relation part of it? Okay. So, I think this is, can I see the square model? Yeah, okay, this is the mild one in the top left. So, we're going to identify the type of mathematical representation and if it's a function. What representation are we using here? What? A graph, right? How do we know it's a graph? It's quite literally a graph. It is a graphical representation because they are graphs. We can see our lines, so we have graphical, I'm just going to write representations. All right, so now we need to determine if the relation is a function. What is the difference between a relation and a function? It's quite literally written on the board. What is the difference between a relation and a function? It is literally on the board, guys. Alright, so for a function, it's a relation, but for every input, there is only one output. Okay? Y'all got that? It doesn't feel like we do, but we're going to move on a little bit. So, this first graph, would this be a function? Yes. Why? Oh yeah, it's a straight line. So on graphs, let me show you this really cool thing. Really easy way to determine if a relation is a function, and it's called the vertical line test. So, what's a vertical line? Up and down. Looks like this. If I can move my vertical line through the graph, and there is no point where it touches the line at the same time, so here, it's only touching this line once, right? Yes or no?
Yes.
Okay. So, it passes the vertical line test, so guess what? It's a function. What about this one? Does this pass the vertical line test?
No.
No, why not?
It's a circle.
Yeah, it's hitting it 2 times. It's a circle. So if you can see, the input is which? Is it our independent or dependent variable? independent, so it's our what value? It's our x. So looking at our x-axis right here, we can see, I think this is x equals 4. We have a y of 1 and a y of like, I think it's like -5. I can't really tell from here. But for 4, there are 2 different outputs, right? 2 different y values. So we can also use that way, but really simple and easy is the vertical line test. What about this last one? Function or, it is exponential, but is it a function or no? Why? Do it on your paper. You have a pencil, you can do it. Yeah, it only hits it once, right? So would it be a function? Yes, perfect. Alright. We feel good? Doesn't feel like we feel good. Alright, same thing with the tables. Can you do a vertical line test on a table?
No.
No. Right? You're not visualizing anything. But, what's a way you guys think we could figure out if it's a function or not? By using tables.
Can we let them, just make predictions,
Oh,
go to
yeah.
vertical services and make predictions and tell them
Sounds good.
Okay.
Alright guys, go to vertical services and make predictions about this one.
that? So you just got 3 tables. We want you to figure out, come up with reasoning for which one you think is a function and which one is not.
Function.
This one?
Where are we going?
Oh,
I am right there.
can y'all wake up? It's terrible. Oh.
Wait, so we're gonna make an our prediction of what it is?
Yeah, on if it's a function or not. All of them.
Andrea, are you talking with your group? You just
No, I know the first one you're gonna use, that's what I put it up to.
But you gotta talk, does your group know? Does everyone in your group know?
So, we didn't say it was repeated as a function.
No, but like,
That was just finding if it was linear or exponential.
but there's a function.
Linear and exponential are both functions, yes.
So I can do it with
You could, but I would go back to the definition of what a function is. Come up with something, y'all. Anything.
This one. What do we think? You're actually doing more work than you need to. No. You just wanna know the rest of it? Hold on, that's good. But what did we ask? Is it
Here, like prediction of this function and other
a, it's in the packet.
for all 3 of those tables.
Yeah, the packet of things on your desk, did she? What do we ask? Is it a what? How can we figure out if it's a function? Way more than
Why
one
is it
minute.
not a function?
What do we always need to go back to figure out if something is the thing?
Okay, but what's the definition of a function?
It's the, starts with D,
It's only one, right? A relation is
you always
infinite.
want to go back to this thing.
So is there an
It
easier way
is
you
the
can
core
do
of
this?
math and of learning, so I'm looking for a piece of.
Hey.
Hey! So say hey?
Yep.
Oh, okay. What do we think of? What do we got?
I don't understand. I don't feel
What's the definition?
Okay.
What is the definition of a function?
Because we should have written it down, guys.
For every input, there's only one output. So when we had our
It is
circle.
a special type of relation.
Oh.
Such that.
Oh, explain to
Yeah,
them what
please
you
explain.
did.
Yeah,
I get it. Why are those functions and not functions, guys? Right up there, how you found that out, how you decided that.
One, and I always say it as, because it's the definition, and only one output.
Oh.
The reason why we say it that way is
We
because
gotta
Like, how do you
one
find out those
guy
are
that
functions and not
needs money
functions?
could be more.
Yeah,
So, but
we got
it
it.
has one,
Alright, what is the definition of a function?
okay? So I want you to look at
We
that.
figuring out what we figuring out.
What's the
For every
output
input,
for
there's
negative
only
three?
one
That's
output.
a bunch.
Oh, I got it.
Which one is your
Does
input?
negative three have any other outputs? Okay, what's the negative two have?
Is your x.
Does it have any
Which
other
one's your
outputs?
output?
So does
So,
every
For
input
every input, for
have
every
one and
x,
only one output?
there's only
That's
one
it. That's what I go back
output.
to,
Why?
the definition.
So, go back to
That's
that
how you get the house.
and look at your tables and see if you can
Okay.
figure that out.
So talk about it, figure out which ones are functions.
Hold on.
which are not. So what are y'all thinking?
Please tell me we got it right.
So it's.
Come on, what did you discover? What was your,
What do we
oh,
actually
The
did is
numbers
a
are going
function,
down,
right?
like-
So
Oh, I
the
have-
exponential function.
So these are your
And that's cool and all,
inputs.
right?
For every input, there's only one output.
Wait.
What did we
But-
discover now? What did we just
Wait,
discover?
You're saying-
What do you mean? What do you mean?
Okay, so
These are not functions, but these are like, it's going down like.
So be careful, we're actually.
Why-
gonna talk about this
why would that
pretty
not-
quickly. So
why
what
would
you're
that not
looking at
be a
is
function?
just the outputs. But you need to always go back to the what. What are we trying to figure out at the end of this day?
What is the definition?
What is it a function? What was the definition of a function?
What is that
Just
mean?
inputs, outputs. That's a
What is-
relation. It is
what
a
does that
special
even mean?
relation.
Because I'm just trying to understand what that means.
Each input.
I was a
So it maps to.
I know, it's terrible.
Maps to one.
Which one's your input?
And.
Which one's your output?
Output. Now,
So
I'll say this, and exponential
for
is always a
every
function.
x,
However,
There was only
notice,
one.
we're only talking about outputs, we're
What
not
does
talking about the
that
inputs. Gotta go to the inputs. What does negative three map to?
Okay, so.
Does negative three map to anything else? What
Alright,
does negative two map to?
so
Does
here's,
it map to anything
one.
else?
are these the same?
This is,
Are these the same?
why? Because each,
Or negative four, those are the same?
No.
wait, no, this is what I go back to.
No, they're not.
But your
The
input is the
definition
same.
tells us
But
what
out-
the thing
But
is.
your output
When
is
you hear
different.
this word,
It's always the
that's what needs to go through your head.
One in,
Gotta go back
But
to
ain't
what
none of
the thing
these
is.
the same.
Hold on,
That's the thing,
hold on.
this right here,
Alright.
this can't be a function because that's a negative one.
So
That's
keep
a
looking at the
four,
others.
But this is two negative threes.
Okay.
So
So
does that
one thing I
mean
want you all to be careful about with this reasoning up here, I just want
Alright.
y'all to look at this. When I'm looking at this,
So,
It's not the same.
there's only one output for every input.
let's look at our
But then what do you
tables.
want?
So what is the definition?
Where's your
of a
input
function?
here? Is it just implied?
Every
Can't
input,
imply.
there's only one
Because
output.
what
So,
do we always want to go back to?
Here's-
What?
another marker.
So the D, I've written it twice over there, the definition, right? You
So,
gotta go back to the definition. What is the
For every
definition that we
X.
don't have written down?
right, that's our input,
It's multiple.
only one
It's yours.
Y.
Yeah, because you were supposed to have already written it down. Yeah. What's a relation?
Output, right?
There's a mapping of two
What we
things.
talked about. So, what does
What's a
that mean?
relation? Mapping of, no, but what are those two things called?
So do you remember we were talking?
Those
there
words
we
are up
had
here somewhere.
a circle, right? We had our center, it was around,
And input and output. And then, by the way, I don't think anyone's hearing the voice of God right now, otherwise we need to have a conversation.
So only one in the five.
We need to come up with reasoning up here,
Maybe one.
okay?
This
God
was-
bless
was
you with
this
the
a
brain
function or
and
not?
use the brain, not jokes, okay? So,
Why not?
relation maps inputs to outputs. So what's a function? I've written that definition over there twice. You need to
What was
write
that
this
thing we talked
definition down.
about?
Just learning math, I want you to do what three things? To think, there's a C word and then another C word. That was the last C word. So think, communicate, collaborate, right? Like, you gotta do those three things. And I wanna point this out. You know what the starting point of thinking is? You need something in order to think. You need what? Context? Okay, maybe. Concepts. But in order to understand, to have those concepts, to then be able to communicate that, do you know what you have to have? It starts with an L. That's not an L. You have to have
Language.
Language. I know most people don't think about mathematics as languages, but I need you to understand every group that I went and talked to, what did I tell you to go back to? The definition. Like, when you are learning something, you've got to focus on the language of the thing, because that term, relation, and that term function, that Ms. Kowalski asked y'all to write down, and I walked around the room, and I don't think I saw a single person who had both those terms written down, maybe one or two. I said maybe one or two, sorry, y'all had it, okay? Around here, we did not have it, right? Like, if you don't have the language, how are you gonna think, communicate, and collaborate about it? Like, guys, the definition tells you what the thing is, and you need to go back to that every time. That needs to be the foundation for what you are doing, okay? I know that we're not used to focusing on language, but like if we are imprecise with our language, what you looking for?
His pencil.
Oh,
It's just gone. I lost it.
gotcha. If you are imprecise with your language or you don't know what the terms mean, then you're not going to be successful with the math. The way you fix it is you learn to think, communicate, collaborate, but you got to develop your language with that. And I will say this, are we defining some of these things for you? Yes, but a lot of times, me defining it for you is not going to help unless you practice using it. And what I mean by that is like, when my son is developing language and the ability to communicate with us, I don't lecture to him about the word function, mostly because that's not developmentally appropriate, but I don't lecture to him about what a pouch is, right? The little things that have like applesauce or something similar to that in it, right? But I go, hey Alex, do you want a pouch? And by talking about it and communicating about it and experiencing the thing, he learns what it is, okay? I need y'all to think and communicate and experience what the thing is, and that's how you're going to get better at this. But y'all are more developed than Alex is. I can give you a definition. Ms. Kowalski can give you a definition, and we need you to go back to it. Everybody was talking about outputs, or they were talking about inputs, but what does a function have to have? Both, and it has to be such that each input maps to one, and only one output. If it's just an input mapping to an output, what do we call that? A relation. Yeah, right? You gotta think, you gotta communicate, you gotta collaborate. Guys, the more you talk about it, the more you communicate about it, the better you're gonna learn it. Now, once again, I need you to remember, is it okay if we mess up? Yes. Do you know what one of the most important parts of learning is? Messing up, right? Like you gotta get outside the brain of like, oh, I gotta get it right or I'm not doing it at all. No, that's the wrong way. That's how you don't learn. The way you learn is by screwing up and learning how to fix it. Okay? So, let's get back into this. And Ms. Kowalski, you haven't talked about the graph side of this yet, right?
No.
You want me to talk about that real quick, or did you got it? Go for it.
Oh, we're talking about vertical lines, yeah.
Right, but I was just gonna say, I just want to point.
Creating graphs?
I was gonna say,
Yeah.
do you know where these graphs came from, guys?
Numbers.
The numbers. -3, 4. There's an x of -3, a y of 4. -4, 3. I want you to notice, can I make a graph out of that table? Can I now use my vertical line test? Remember, use your mathematical representations. You don't have to stay stuck on what you have. I will say I go back to the definition, because once you learn the definition, that table's really nice and easy. Okay? But think about those things.
Okay, so looking around the room, it looks like we're all pretty solid on that first one, right? It's, for every input, there's what? One output. -3 goes to 16, and Mr. Kinney wonderfully drew our graph. Does it pass the vertical line test?
Yes.
Yeah, crazy. All right, 2 tripped a couple people up. Okay, this was a little tricky. Who thought it was a function? Raise your hands. I see a lot more functions written on the wall than that. Okay, who thought it was not a function? It looks like the 8s thought it wasn't a function. Looks like, I don't know about if the Kings figured it out. So, why did you think it was not a function? Number 2. Why did we think it was not a function? So there are 2 repeated outputs, okay? But what does the definition say?
One input per output.
one input, for every input, there is only one output. So what this is there are two outputs that are the same, right? But do they have the same input?
No.
They have two different inputs, and we get, for every -2, we only got 0, right? For every -1, we only got 0. So it's okay that we repeated 0 as an output because they have two different inputs. Does that make a little bit of sense? But an easier way to figure that out when it gets tricky like that is what? The vertical line test. Does it pass it? I only heard one person say yes.
Yeah.
Yes, no?
Yeah.
So, is there ever a point where if I'm drawing lines, the line crosses through this figure twice? No. It only hits it once. Because every input only has one output. Okay? Just because we have the same output for two different inputs, that's okay. But what if we also had on here, I'll show it over here. That makes more sense. So 2 is a function. Because for every input, there's what? Only one output. Now, it looks like we all were good about 3. Why was 3 not a function?
There's different output.
Yeah, so the input of 3, or sorry, -3, what were its outputs?
4 and -4.
We had 4 and -4. So for every input, was there only one output? No. Okay? Same with 4, same with -4, we had -3 and 3. And then once again, we have our vertical line test.
Nope.
It crosses through twice. It doesn't pass our vertical line test. So, it's what? Not a function. Perfect. Okay. I would write down about number 2 if we got it wrong or confused about it. What we wrote on here. Perfect. Do you want to do this one?
Yes.
Okay. So in I think it's in the spicy.
Yeah.
Alright. Our spicy problem, what are we given, guys? We're given equations.
Did someone say, oh Lord?
What is something we could do with an equation though?
That's all it is.
Okay, you can solve an equation, yes. Do we have to stick with an equation all the time? No.
Really quick question. What do you mean by solve an equation?
Figure out the answer. Give an answer.
How do you figure out the answer here?
Work it out.
What do you work out?
The equation.
What do you work? Okay, so I want y'all to see, like, I need y'all to hear me clearly on this. Like, we don't have a precise understanding of what the word solve means, I think, and that's going to get us into circular logic, okay? I'll go ahead and tell you this. You can't solve these equations. What I mean by that is the way that you think about the word solve is not what you're doing here. The word solve can be applied to this equation. No? Yeah. Alright. I can solve this. What would I do to solve this? Subtract 7, okay? As I did to both sides, why?
Because you have to.
I subtracted 7 here to create a 0, that's the inverse. Why do it to both sides? We taught this last
Yeah.
week.
Get rid of it.
Make sure both sides are the same.
So make sure the equations stay the, that's called that property of quality. What does 3x equal? 15. Now what do I do?
Divide 3x.
Divide, ooh, not quite.
Divide 3 on those.
I would divide by 3. Remember, I want to know what x is. So remember, and I've actually started to talk about this with another group. Remember, I like to do the reciprocal here, 1/3, 1 divided by 3, because what's that fraction bar mean? Division. Remember, it helped us with that exponential function a little bit later, so these two groups right here can vouch for me. It helps when we talk about exponentials to start thinking about this as division. What's 1/3 of 15?
5.
Okay, that's solving. What did I do? I didn't just find an answer. And I know that that's what we're used to saying, but let's say I screwed up. Let's say I found x equals 7. I found an answer, right? But I didn't solve it because that's not my solution. Does anyone know why that's not the solution? Beyond just that the solution is 5?
Because you took the wrong section.
Not just that. Ms. Kowalski, why is that 7 not the solution?
Do we like actually say why?
Yeah.
Oh, if we plug 7 back in, are we gonna get 22?
So, I need y'all to see this calculator up here, right? 3 times 7 plus 7 equals 22. Notice I can type that equation in. What's it going to tell me? False. So how do I know it's not my solution? Because that statement is
False.
with these calculators, you can go up and highlight it. You can hit enter now and change that 7 to a what? What's it supposed to be?
5.
What does it say? Guys, the word solution in math only means what makes the equation or inequality true. When we say solve, we mean find what makes the equation or inequality true. How many variables can I do that with right here? Or how many variables did I have here?
2. 1 to 1.
I only had 1. You can only solve an equation if you have the same number of equations as variables. I can't solve this. What can I do? I can make something else, but I can't solve it.
You can make a graph.
Oh, I can make a graph. Okay. What else could I make?
A table.
A table. I can look at inputs and remember, we got to go back to the definition. And so please understand, like, this is why some of us have trouble. And I know Ms. Kolsky is teaching this, but I'm just trying to focus on this language side of it. If you don't have a precise understanding of the language, it's going to affect your ability to be successful later. Because if you think about solve as anything but what we just discussed, you're not going to be able to work on this problem. You're not going to be able to find out if it's a function or not, because we're not solving anything. The language matters. And guess what? And I want y'all to hear me on this. Every single one of you is capable of learning language. That's why I know every single one of you is capable of learning math. Think about it. It's just a language to allow us to communicate. Right, Wayne? Oh, there we go. KJ? Uh-huh.
You guys are never gonna guess where you're gonna work on these. Vertical surfaces, that's crazy, let's go. Figure out if they're functions or not. Use your resources, use your tools, use the definition. Oh, gets us up.
We need people like KJ to wake up. What?
Only one output. I like up here they wrote exponential curve, so you could graph it on your calculator. I showed a couple groups that. Another way we know, guys, what were we talking about all day yesterday?
Graph.
I don't think we talked about graphs once yesterday. What were we working with yesterday? We're working with equations. What are the names of the two things we've been focusing on?
Slope and the y-intercept. Stuff like that.
Linear and exponential.
Oh, yeah, that.
Yeah, that's what we've been focused on. And when we talk about linear and exponential, what do we call those things? A function. We say linear and exponential functions, right?
Yep.
So, can you guys look at this and think, what does that look like?
Exponential function.
An exponential function. You have your exponent, You have your rate of change and you have your intercept, right? So, this is where we need to correct what Ms. Kowalski told y'all yesterday. So, do you remember yesterday we were talking and I did m to the x times b for your exponential function? That's not how we're going to represent that. We're going to do a times b to the x. It looks the same, but an exponential function, it's not, the m is not our slope. Okay? We don't have a rise over run in an exponential like we do in linear. It's not going to be constant.
And the only thing we mean in math by m is, what's the thing? Yeah,
Slope.
m only means slope for a linear function. So Ms. Kowalski and I talked about that.
Yeah. See, I'm learning too, y'all. I was racking my brain all day yesterday about what that function was, and then when Mr. Amy got back, I figured it out. So, what is our b here? Alright, so in this specific example, I'm going to write it over here. In that specific example, it is 2 over 3. But what is the b representing? So, in y equals mx plus b, our b is our y-intercept. And what's our m?
Slope.
Slope, okay? What if we also been using multiplication as what? What is multiplication?
Repeated addition.
Repeated addition, right? So that's why you're multiplying m times x, repeated addition. What are we doing here with b?
Repeated multiplication.
Repeated multiplication, right? Because of this exponent, we have repeated multiplication. So is this b going to be the same b we have here? Is this b going to be our y-intercept? No, what is this b?
Slope.
We don't have slope in an exponential.
It's the repeated thing.
It's what?
Thing that's being repeated.
It's the thing that's being repeated. What do we call that when we have a table? It's repeated multiplication. Oh. We have inputs and outputs in a table. It starts R,
Rate of change.
rate of change. This is our rate of change. It's what we are repeatedly multiplying, right? What we are repeatedly, I would be writing this down because none of us are, we're not immediately answering, we don't know these things, we should be writing them down so we can remember them, we have something to look back on. And then what would our A be? This would be our y-intercept. Me and Mr. Kinney were also talking about this yesterday. Y equals. What does this look like? What? Linear. It looks a lot like linear. It looks like y equals mx plus b flipped around, but this way we can, this is just another way to put it, if this will help you. If not, you don't have to. But this way our b's are the same. Our b's are what we are repeatedly adding and repeatedly multiplying, our rate of change, and our a's are our y-intercept. So that's just to see how those connect. But if you guys can stick with y equals mx plus b, it's just to see how the a and b connect with the exponential.
I will say this, when teaching students, because you're used to y equals mx plus b, that's what I use. Personally, I really like the y equals a plus b mix, because it literally tells the story of what's happening. I'm starting at my y-intercept a, and then if I repeatedly add, it's plus bx, because b times x is repeated addition. If it's repeated multiplication, I start at a times b to the x, because it's repeatedly multiplying.
Perfect. Go
Okay.
ahead.
Did you name what we call that thing we're repeatedly multiplying by?
The rate of change?
But what was the, so no, not the
So
name, the
no.
constant factor?
Oh, no, I didn't. Yeah, I'll do that.
So remember how
We should have tabled.
the constant additive rate of change has a name? What's the constant additive rate of change called? It is repeated addition, but there's a name for it. The thing that we only use M for. Slope. The constant additive rate of change is our slope, but we also have a name for that constant multiplication.
Oh, you mean saying
Yeah.
it? It's our,
I'm saying you
our factor. Our common factor?
constant factor.
Constant factor.
We, did anyone here have Miss Williams last year? So y'all talked about geometric sequences and common ratios, right? Does that sound familiar? It's the same thing as a common ratio. Okay, so we call it common ratios, but a better term when we get to continuous functions, constant factor. Because what does that word constant mean? I just realized we should have talked about that better. That's my fault. Hey guys, if something's constant in your life, what does it do?
It's repeated.
It stays the same, right? Okay, so it's repeated, yes, but how is it repeated? It's staying the same. You see that now? So a constant factor, because Ms. Kowalski, what do we do with factors?
We multiply them.
Notice the language again matters. If you understand that we multiply factors, we are constantly multiplying, not just changing, because it can change how it depends on what type of function it is. We are constantly multiplying.
Also, guys, I want to point out, did we go over this yesterday? Did we get into this nitty gritty?
Nope.
No. Because Mr. Kidding wasn't here to explain these things to me. I am also learning with you. I'm not going to lead you astray. It's not like I don't know the math, right? But there are some terms, some things that I need to brush up on that I need to learn. So I'm learning with you. We're all in this together, right? We got this.
I was like, I will agree. Mr. Kenny's crazy. He's different. I get that.
He's like,
but
so smart.
I promise you, I understand. I've done a lot of diving into these things to figure out ways to help you learn it long term, not just get through a test, but for it to be a long-term useful thing. And there's research that I've actually done personally on being very precise with your language. And there's research that shows if you develop your precision with this language, with Kowalski, you did not get taught like that, I don't think.
No.
Nobody does. But the more precise you are with your language, the better you learn it, right? If you're able to communicate it about something better, the better you learn it. I think, Lane, you were the one I was talking about, in this group I was talking about, like, the more you
communicate, the better you learn it, and the more you get used to it.
right, the more you communicate, the more you get used to it, the better you're gonna learn it. So that's why I'm so intentional about language. If you don't understand the language of mathematics and understand it well, that's when students get lost and they get frustrated, and that's what I don't want to happen. And I know that initially the language part of it can get frustrating. It's like, Mr. Kinney, there's so much, but I promise you, the better you learn it from the beginning, the easier it gets over time, because you learn to be more precise with it constantly, over and over and over again. Okay? So please trust me on that. If you gotta make flashcards, make flashcards for the vocab. If you gotta do a Quizlet, make a Quizlet for the vocab. If you're good with just reading over your notes for 5 to 10 minutes a night, do that. But like, do something so that you learn the vocabulary well and you can always go back to it.
Why didn't you answer here? Alright, so we looking at that one. What is it? What kind of function is it? Exponential, right? We just talked about that. We literally just talked about it. What about this second one? Linear, how do we know?
Wait, regret.
It does say it on the
You're
board,
not,
but just looking at this,
you're not multiplying.
what does it look like?
You're not multiplying.
You're not multiplying, what do you mean you're not multiplying?
Well, but for the exponential one, it's got like a little multiplication thing on the.
Okay, yeah, you're not, but what about this form?
It was like an x plus b.
Right, it looks a little like y equals mx plus b, right? I mean, it is saying b minus mx, that's the form. But are these equivalent to each other?
Yeah.
Yeah, except this is a negative slope, right? You have a negative n. You have a negative slope. Okay, so that's function. It's a straight line, passes the vertical line test. This last one tripped some of us up putting into our calculator. We were trying to graph it, and when we were graphing, what did we hit to type in our equation?
You want me to pull the calculator?
Yeah, you can. That'll make it easier.
Representation.
What? I mean, yeah, we all should have gotten a circle.
So don't forget, create a graph page. Do y'all remember how to create new pages? Okay, does everybody have a calculator in hand to look at and refer to? So Maja, where's your calculator? Jordan, Jacayla, Bree? Oh, it's close in hand. Okay. Calculators in hand. This is not for kicks and giggles. I know how to do this. I need you to know how to do this. Ms. Kowalski needs you to know how to do this. Again, the better you learn this now, the easier your life gets later. And we want your life to be easy later. Not necessarily here in the short term. In the long term, I want your life to be easy. Notice, only a few years. He said, how old are these things? This version, I will say, is only a few years. These calculators have been out since about 2011, 2012, right when I first started teaching. That's when they came out. Maybe a little before that. Anyways, please notice what notation's up on that board? F of x, that means, did we name that type of notation earlier?
Yeah.
Oh, we named it as function notation?
Yeah.
Okay, so it's function notation, so what do you gotta have? A function, there we go, right? Using that language, okay? Do we know that x squared plus y squared equals 25 is a function?
No.
No, so I'm gonna hit escape. Hey Jordan, what's the button that lets me do cool crap? Every time. They just told you, bro. Come on, what is it? What was it? What was the button that lets me do cool crap? Menu! Yeah, menu! Menu pops up a whole bunch of cool crap. And if you read through the options, I didn't tell Bree earlier, Bree, you just saw it. What was it? Yeah, I'm going to create a graph. Anyone see an option other than function that might be kind of useful?
Relation.
Oh, see how that language matters, right? When we understand our language, our definitions, it's okay, I can go to relation, and it's blank, because I can type in whatever I want. Be aware the equal sign is here next to the trig button. So if you look at control and below it, there's an equal sign. X squared plus y squared. Man, that's really easy to look at. Just gotta create a graph, guys.
Is this a function?
No.
No.
Why?
It's a circle. It's a circle.
It's a circle,
Fails the line
so
test.
doesn't pass the vertical line test. This line isn't big enough. It hits it twice. Does not pass. Yay. Okay. Perfect.
Now we got 10 minutes to do what we plan to do.
We gotta run through this, guys.
We're just gonna, I would just jump into number 4 since we talked about linear and exponential so
Yeah.
much.
Okay, perfect. You guys should now know the difference between a relation and a function. You know your mathematical representations, or at least you better. That's all we've been talking about. Linear, exponential. Do we know what equivalent means?
Same or equal.
The same, equal. So equal to.
Things can be equal without being equivalent.
Yeah.
Sorry, but like here, these things are equal. They are not equivalent. Okay? Things can be equal without being equivalent. How would you explain equivalent?
I was thinking like, I don't know.
Oh, how about this?
You could explain it.
See this equation right here? You see this graph right here? Do they look the exact same? Well, no, because one's a graph, one's an equation. But they're equivalent.
So it's got the same meaning to it.
There we go. What were y'all saying? Right, because they have the same what?
Meaning.
Right, like that's what equivalence means. They may look different, but they're telling the same story. Specifically, when we talk about functions, the same inputs are mapping to the same outputs. We talk about functions, that's what we mean by equivalent. the same inputs map to the same outputs, but they have the same meaning. That's a really good way to say it. Okay? So I might make a note of that, because once again, language, when Ms. Kowalski says equivalent later, you gotta know instantly what that means. Or stare at me and don't write that down, that's your choice. I love it, Mason's writing it down. I got two people, Bree's got it written down. Tyler's thinking about it. There we go. Oh, we got all of three. Samija now, we got four. What does equivalent mean? So the same inputs map to the same outputs, or as Mason said, they have the same meaning. They may not look the same, but they have the same meaning. Equivalent. They may not look the same, but they have the same
Okay,
meaning.
then.
There we go.
There we go.
Hey, by the way, while y'all are writing it down, anyone that I can get to volunteer for Hero Friday this week?
I did mine. I'm out.
Basically, I'm done. Peace. I heard Bree wants to do it. Does that sound good? What?
No.
Why?
No, not yet.
Not yet?
Probably like in another week.
I do it.
Yes.
I do it.
So, like, what is-
Then switch back to your slide.
Nope.
Alright guys, we're about to run through this. Done, talked about that. Perfect, yesterday we talked about what makes a relation linear, what makes a relation exponential. We now know it's not a relation, it's a what? Function, perfect, alright. So those, alright, 4. We did not do this one yesterday, maybe some groups got this far, but I don't think so. This is from yesterday, the what comes next, what comes later packet. We're gonna quickly go through this one. You weren't here yesterday?
We can also, like, we're not going to do that tomorrow, do you think? Let's just let them know about it. Yeah, I know. I said we haven't gotten 4 yet. I mean, you have 4 on the packet I gave you. We didn't do 4 yet. Right?
We got
You
this.
said that we had extra time.
If you could do it, then do it.
Oh, did you guys do 4?
Yeah.
Oh, perfect. No. Perfect. If you didn't, go keep working through the packet. If not, start on 4 or 3 or 2 if you didn't do any of it. We're going to use the last little bit of time to not pack up. We're going to use the last little bit of time to work on this.
Sounds good to me. Let's go.
Hey, I do, but that's what I do. Yeah. I mean, so
Yeah. There's a clock on the wall.
We got 5 minutes left. Let's go. We got learning to do.
Oh, guys, real quick, me and Mr. Kennedy talked about this morning. I want to talk to you guys about this. Okay. What we were doing yesterday, what were we doing to find our rate of change? We were subtracting, right? And I was just doing this, 6 minus 2, 4. We're adding 4. But what if we didn't have x of 2, it just went from 1 to 3? What would the difference here be? 16. Would 16 be our slope? Why not? Why would 16 not be our slope? Any ideas? Output? Okay, what is slope? Guys, what is slope? Rise over run. Or what else did we talk about? The change in y over change in x. Okay? What is our change in x here?
2.
2. What is our change in y? 16. So what would our slope be? 16 over 2, which is what? 8. So I want you guys to make sure when you are analyzing tables, when you are doing your slope on your table, you are realizing how the x is changing as well, not just the y. Because we could trip you up and have the table that goes 1, 3, 5, 7, 9. And if you don't make sure you're recognizing your change in x as well as your change in y, then we're not going to get the correct slope. So what's the change in y, or change in x from 5 to 6? 1. What's the change in your y from, we're going to use 3 and 4.
No, that's fine. 324.
Okay, 324?
Yeah.
24, and this is 1.
I would say,
This
quick
is-
question.
Yeah.
Any guess why those numbers don't even come close to matching up?
Because it's not,
It's not what?
it's not linear or.
I would say it's not adding,
Yeah.
is it? Oh, so it might be multiplying. So all that to say, check your rate of change for sure.
Check that.
But we're only adding like that in linear and what are called polynomial functions. We'll study later. May not be linear. In fact, I don't think it is.
I realized that when I got down to 5 and 6.
I was
trying to
wondering
just
if
to
you-
double check. I didn't look.
Yeah. I was wondering.
Double check when you're working on things, guys. Or else you're gonna end up like that.
By the way, do y'all know another way besides, just because we only have a couple minutes left, do you know of another way besides just looking at the rate of change to figure out what type of function it is? None? Who said you had to stay at the table? Oh, you could have made a graph out of those points? Could that have helped? Did we ever say you had to stay at a table? In fact, tomorrow when we pick up with this, you know what we're gonna make you do?
Make a
Do
graph.
some graphs, you know why? Because it's good for you. Oh,
Oh.
good thing we're gonna record a class and you already have the resources you need, right? Oh. Better prepare for DYU on Friday. What? Yo, we've almost got a week on linear and exponential functions.
When we learn something, we're gonna do days and we move on to the next.
Y'all, it's been 4 days on just linear and exponential. I want you to think about that. 4 on just linear and exponential. That's a lot of time. We gotta do a DYU on Friday. Tomorrow's day 5. Tomorrow's Thursday.
STPA tomorrow?
Yeah.
KJ?
I'm ready.
STPA tomorrow? Do you need a new one? Do you need a new one?
No.
Okay, perfect.